Hello friends, Mr. Burrell here. We're in the end of our unit talking about exponents. We've talked a lot about exponents, different kinds of things we can do with exponential expressions, how we can simplify them, how we can rewrite them, transferring between like exponential form and radical form when we have fraction exponents. We've talked about a lot of different properties and a lot of different rules. So we're going to wrap it all together talking about rational exponent rules. So by the end of this lesson today, this is what I hope you're able to do. I want you to be able to apply all the exponent rules that we've talked about, all the exponent rules that you now know, to rational exponents. When I say rational exponents, what do I mean again? Well, a rational number is a number that can be written as a fraction. So when I'm talking about exponent rules with rational exponents, I'm talking about applying the rules that we've discussed with exponents when those exponents are fractions. So, just as a reminder, let me move my face out of the way so you can see a little bit better. Here are some of the main rules that we've discussed throughout this unit, talking about exponents. When I multiply exponents with the same base, I add the exponents. So like x squared times x cubed, that was equal to x to the fifth, because I add 2x's plus 3x's to get 5x's. When I divide exponents with the same base, I subtract the exponents. So if I have something like x to the fifth divided by x to the third, 3 of the x's in the top will cancel with these 3 x's in the bottom, leaving me with x to the second, or x squared. So I subtract those exponents. If I had negative exponents, when I have negative exponents in the numerator or in the top of a fraction, they move to the denominator, or the bottom of a fraction. So we talked about if I have like x cubed over y to the negative 2 or something, that becomes x cubed times y to the positive 2. This negative exponent flips the line and changes the sign to a positive. Same when I have, that was when it was in the denominator, so when I have negative exponents in the denominator or in the bottom, they move to the numerator, or the top of the fraction. So the phrase that we've been using is flip the line, change the sign. Flip the line, change the sign. When it comes to negative exponents, we flip the line and change the sign. We also talked about zero exponents, how when I have anything to the 0 power, it's equal to 1. And then one of the last exponent rules we discussed is that when I take a power to another power, I multiply those powers together. So if I have something, say, like x squared times y cubed to the third power, that would become x to the sixth times y to the ninth. Because each of these powers, when I take them to another power, they're going to multiply. So that turns into x to the sixth, y to the ninth. Those are all of the rules that we've discussed when it comes to simplifying exponential expressions in this unit. So all of these same rules apply even when the exponents aren't integers. So if you come back here, all of these exponents were integers, meaning they were like either positive or negative whole numbers. So like 2, 3, 5, negative 2, negative 4, 6, 9. Those are all integers. What if they aren't integers though? What if I have exponents that are fractions? Can I still apply those same rules? Yes, I can. So before we get into using the rules of like adding exponents, multiplying exponents, let's remind ourselves how we add and subtract and multiply fractions real quick. So when I add fractions together, like 1/2 plus 5/2, the denominators have to be the same. So 1/2 plus 5/2, I can add those together because the bottoms of these fractions are the same. 1/2 plus 5/2, I add the tops together, that gives me 6/2. Or 6 divided by 2 would be equal to 3. So 1/2 plus 5/2 is 6/2, or 3. 1/4 plus 3/2, I can't multiply those together as is because I need a common denominator. Well, this is 1/4. This is 3/2. If I multiply the bottom of this fraction, that'll make a 4. But if I multiply on the bottom of that fraction, I have to multiply on the top as well. So that would be the same as 1/4 plus 6/4, which would be 7/4. So 1/4 plus 3/2 is the same as 1/4 plus 6/4, which is 7/4. When I multiply fractions, I don't need common denominators. I can just multiply straight across the top and the bottom. So multiplying 1/2 times 5/2 would be 5 over 4, because 1 times 5 is 5, 2 times 2 is 4. Multiplying something like this, 2 times 7/5. 2, remember, you can write as a fraction of 2 over 1, so 2 times 7 is 14. 1 times 5 is 5. So my answer there would be 14/5. 1 plus 4/3, I write that as 1 over 1, which means I have to multiply the top and bottom by 3, which would give me 3 over 3 plus 4 over 3, which when I add fractions, I add the top and leave the bottom the same, so my answer would be 7/3. And when I multiply these fractions together and multiply the top and the bottom, I get 15 over 6. So that's a really brief review of what you learned a little while ago about how to add, subtract, and multiply fractions. But I'm not here technically per se to test your ability to add and subtract and multiply fractions. I'm here to test your ability to simplify exponential expressions. So when in doubt, you can add and subtract and multiply fractions in your calculator. When doing that, you just need to put all your fractions in parentheses. So like if I was doing 1/2 plus 5/2 in my calculator, I'd put parentheses 1 divided by 2, parentheses, because that'll give me 1/2, plus parentheses 5 divided by 2, which would give me 5/2. And in my calculator, that will simplify the fraction for me. Also a reminder, in our calculators, or if you're using another calculator, the commands might be different. There's also a way to change a decimal to a fraction in your calculator. When you have the decimal in your calculator, you've pressed enter and you have the decimal as your answer there. Press math, enter, enter. It will take you to a menu that will convert that decimal into a fraction. So that might be helpful in going about some of these problems if you're a little bit queasy on adding, subtracting, and multiplying fractions. So let's review some basic ones without fractions. So like 2a to the second times 4a to the fourth. When I've done in the past, I've kind of accordioned this out, right? 2 times a times 4 times a times a times a times a. I don't need to do that. I can recognize that 2 times 4 is 8. I multiply my plain Jane numbers. And then a squared times a to the fourth. A squared times a to the fourth is a to the sixth. I count up all of those. I add them together. So this would be 8a to the sixth. 1, 2, 3, 4, 5, 6. 8a to the sixth. This one right here, if I was doing it before, I would have accordioned it out. 4p times p times p times p times p over 3 times p times p times p. And 3 of these p's would cancel out, which would leave me with 4p squared on the top and 3 on the bottom. But I didn't have to accordion it out. You probably notice that 5p's minus 3p's gives me 2p's. So I subtracted those exponents together. Here, x to the third times x to the second power. Well, first of all, in this little parentheses, x to the third times x is x to the fourth, because 3x's plus 1x is 4x's. And then x to the fourth squared, I can either write x to the fourth times x to the fourth, because x to the fourth squared is just x to the fourth multiplied by itself. Or you can recognize that 4 times 2, when I multiply these together, it gives me x to the 8. 4x's and 4x's give me x to the 8. So those are a lot of the basic rules with exponents that we've discussed. So, now let me show you these. What about these problems? These ones no longer have integer exponents, they have rational exponents, or fractions. A lot of these have fractions, see? So the principle is going to be the exact same. So with 2a to the 2/3 power times 4a to the 4/3 power, 2 times 4 multiplied just like normal because they're plain Jane numbers, which is 8. A to the 2/3 times a to the 4/3. When I multiply exponents with the same base, I'm going to add them. So I'm going to take 2/3 plus 4/3. Well, what is 2/3 plus 4/3? They already have a common denominator, so I'm going to add the tops and leave the bottoms the same. So 6/3. So 8a to the 6/3. And I would give you credit for that, but also recognize that 6 divided by 3, either if I type that in my calculator or just do it in my head, 6 divided by 3 is 2. So I could simplify that and write it as 8a squared, or 8a to the second power. Okay, so when I multiply exponents with the same base, I add those exponents together. How about 4p squared divided by 3p to the 1/2? Well, when I divide exponents with the same base, I'm going to subtract them. So like my 4 and my 3 will stay the same. That fraction I divide as per usual, but it doesn't reduce. With these exponents, I'm going to have to subtract. 2 minus 1/2, or 2 over 1 minus 1/2. Well, when I'm subtracting fractions, I need to have a common denominator. So I'm going to multiply the top and bottom of this fraction by 2, so I have 2 on the bottom of both denominators. That would give me 4 over 2 minus 1 over 2, which is equal to 3 over 2. Okay, 4 over 2 minus 1 over 2 is 3 over 2. So p to the 3 over 2 power, that's what I have in the numerator here. 4p to the 3/2 power over 3 would be my final answer. If these had been flipped, say this had been 4p to the 1/2 over 3p squared, since the bigger number's in the bottom, then my answer would be 4 over 3p to the 3/2 because the bigger number is in the bottom. So when I divide exponents with the same base, I subtract the exponents. Lastly, here, let's take a look at this. X to the 5/3 times x, in parentheses, to the 1/3 power. Well, first, right here inside the parentheses, I am multiplying. So x to the 5/3 times x to the 1, this is just 1x. I need to, when I'm multiplying my exponents, I need to add them. 5/3 plus 1, or 1 over 1. Well, they need to have a common denominator. So if I multiply the top and bottom by 3, I'd have 5/3 plus 3/3, which would give me 8/3. So, in parentheses here, I have x to the 8/3 power, all to the power of 1/3. Well, when I have a power to a power, what's the rule? When I take a power to another power, I multiply those powers together. So 8/3 times 1/3, when I'm multiplying fractions, again, you can do this in your calculator or just by hand here. 8/3 times 1/3, I multiply the tops and the bottoms. So this is 8/9. So my final answer is x to the 8/9 power. That would be my final answer. Let's do one more. Let's look at this one right here. So I have b to the 2/3 power to the 1/2 power times b to the 5/6. So first I'm going to take care of these powers. When I take a power to another power, I multiply those powers together. 2/3 times 1/2. Well, when I multiply fractions, I multiply the tops and the bottoms. So 2/3 times 1/2 is 2/6. Okay, and I'm going to leave it like that. That fraction can be reduced, but I'm going to leave it like that for reasons I'll show you in a second. So this right here, when I multiply them together, gives me b to the 2/6 power, and then times b to the 5/6 power. So now I have a multiplication problem. When I multiply exponents with the same base, what do I do with the exponents? I add them. I add them together. And I left this as 2/6 because notice they already have a common denominator. So I'm going to add the tops, leave the bottom the same. So this final answer would be b to the 7/6. B to the 7/6 power, or b to the 7/6 power. I encourage you to pause this video and try this one here for some extra practice. But that's it for this lesson. We're using all the same exponent rules that we've already discussed, but now we're applying them to rational exponents. In other words, exponents that are fractions. So I hope that was helpful. Please don't hesitate to reach out to me at all if you have any questions whatsoever, and I hope you enjoyed that as much as I did.